Hi, my name is Yongkyu, and currently I'm working as an assistant professor at Gangnam University. Before joining Gangnam University in this March, I had been working as a network traffic engineer in Samsung Electronics. Personally, I'm honored to present here with my first talk since my academic appointment has started. The title of this talk is an energy efficient operation of computing resources in cloud data centers. Here's the content. The first section introduces some backgrounds of the research study, and the second section will introduce the system model, which is actually a mathematical statement of the problem. And then I will explain a heuristic algorithm to solve the problem, which we will call LPC-ME. In the last two sections, we will talk about some numerical results and corresponding discussion. The importance of data centers is ever growing because most computing jobs today are requested to the data centers. And usually, data center is pretty large scale, which comprises huge number of servers. Therefore, it is not surprising that the environmental effects due to data centers are growing problems in the world. Specifically, data centers are reported to consume 3% of the global electricity and account for 2% of the greenhouse gas emission. The situation now is worse because these numerics are measured in 2014, like 7 years ago. In order to achieve greener but still working well data centers, we focus on the two performance metrics. The first one is the response time, defined by the job's completion time minus its arrival time. In the communications and computing industry, response time is a popular measure that is used to quantify the quality of service. Psychologically, users tend not to recognize difference between two very short response times, but they will definitely notice long response time and easily irritated by this exception. So system operators are trying to guarantee a certain quality of service by reducing the response time tail. Another primary performance metric is power consumption, which is the cumulative electricity usage of overall servers. Of course, the energy efficiency is inversely proportional to the total power consumption for the same amount of workloads. In summary, our research goal is to minimize the power consumption while maintaining reasonably short response times. Numerous research studies have been published for the last decades on this topic. One of the most similar work is a conference proceeding of Liu et al. In 2013, who tried to achieve energy efficiency in data centers as well. The concept is similar, but technical details are different, so we refer you to the proceeding if you are interested after this talk. In 2014, we proposed an analytical framework that combined a network utility maximization algorithm with modern queuing theory that resulted in a distributed algorithm to achieve energy-efficient data centers. We think the framework was quite novel, but it requires some strong assumptions like known a priori traffic property. A very recent A very recent paper of CMU professor Harcourt Barter neatly surveyed the problems regarding data center computing. So we also refer to this paper for the audiences who are interested in. Now, I will move on to describe the system model. Using a queuing theoretic notation, we model the system as a network of time-varying GG1 processor sharing queues. Let's look at the abstract data center. The incoming requests are multi-class in terms of their application types. For example, let's say we have 4 different application types. And definitely, the workloads for each application is time-dependent and non-exponential, which we come up with a non-stationary, non-Poisson process. On the server side, data centers have heterogeneous servers in terms of their power consumption, profile, and hosting applications. Also, it is reasonable to think of the jobs in a server are time-sharing a processor, which is called processor sharing service discipline in queuing theory community. There are 2 decision points for this system. The speed scaling rule for the servers and the routing policy for the centralized job dispatcher. The ideal decision should reduce the power consumption at the lowest level capable of processing all the user requests within a short response time. Here's the notation to state a mathematical formulation. I will not cover all the details, but only explain this chunk by chunk. First, we have predefined sets that associate the hosting information between applications and servers. Applications are indexed by I, and servers are indexed by J. And second, we have time-dependent decision variables that correspond to the routing decision and speed scaling decision. Third, we have server-related parameters that define the power consumption, speed range, and service level in terms of response time. And finally, we have parameters that quantify the non-stationary stochastic computing workloads. The optimization model P1 states the problem of interest. The objective function 1a is to minimize the total power consumption over the planning horizon. The constraints 1b and c ensure the job routing is done in reasonable manners. The constraints 1d and e restrict the server's speed towards completing all the incoming jobs. Finally, the constraint 1f is saying that the arriving job to server J at time t should be completed within a predefined server-specific deadline delta J. If we assume that the optimal values are given, one of the natural usages of them is straightforward. For the routing decision, we just route an application I job to server J with the probability R sub ij star, and adjust the speed of server J according to mu sub j star. However, directly solving the problem is looking limited because of several complicating factors such as non-linear functional objective, non-stationarity, and uncertainty. Instead, we come up with a heuristic algorithm called LPC-ME. So in this section, I'm going to explain the idea of LPC-ME. First, we adopt a generic formed power function for each server. So we assume that server's power consumption is a convex function of its speed mu. Now, a reasonable question is like this. Shorter completion time with higher processing rate, or longer completion time with lower processing rate. Which way is more energy efficient? To answer this question, we state a proposition that proves the latter is more energy efficient. The proposition 1 implies two insights. First, there exists an optimal server speed in terms of total power consumption given a constant job size. Hence, scaling the server speed at the level that is lower than the optimal speed can be rather harmful in terms of energy efficiency. Second, slowly processing a job is more energy efficient in most cases. With this proposition in our mind, we come up with an algorithm we will call LPC-ME that stands for the least power consuming job routing and minimizing earliness speed scaling. I do not explain the technical derivation, but only will deliver the underlying idea through the next two sections. No, next two slides, sorry. I will explain the minimizing earliness first. The word earliness, by definition, means the quality of coming early or earlier in time. So what I mean by minimizing earliness is a speed scaling rule towards finishing the jobs at their deadline as exactly as possible. And the rationale behind this is supported by proposition 1. When it comes to the routing policy, we are motivated by some well-known greedy heuristics called JSQ and LWL. JSQ is to route a job to the server with the smallest number of jobs, and LWL is to route a job to the server with the least remaining workloads. Assuming the speed scaling of each server is done by minimizing earliness, dispatching a job to a server always increases the server speed. Recalling that the power function is convex, dispatching a job to the server with minimum speed must be the most energy efficient decision when all the servers are homogeneous. However, we are considering a situation where servers are heterogeneous. So picking a server with the least power consumption remains still a greedy heuristic decision. Now, let's move to the numerical results. For the numerical experiments, we simulate a virtual data center comprises 10 heterogeneous servers and 5 cloud applications. We synthetically generate the cloud computing workloads using the following parameters. Note that we use sinusoidal arrival late functions to mimic the real-world traffic characteristics that represent elephants and mice effect, which means few applications with heavy traffic and many others with light traffic. Our primary interest from the experiments is the energy-saving performance of LPC routing policy. For benchmarks, we use some other simple routing policies: random, JSQ, LWL. Random routing policy is to choose a server by drawing a fair dice, and JSQ and LWL are as explained in the previous section. We fixed the speed scaling rule as minimizing onlyness, and varied the routing policy for each the same workload instance. Then we run 10,000 replications of 2,000 unit time simulation to get large enough samples that will help us to avoid misinterpretation due to outliers. After all, here comes the numerical results. We draw two box whisker plots to describe the results. The x-axis are routing policies, and y-axis are total power consumption and response time violation probability, respectively. Although the burstiness of user traffic produces many outliers depicted by those cross dots, we can observe a clear effectiveness of LPC in terms of both power consumption and quality of service. Now, let me wrap up this talk with some discussion points. First point is the value of the information. When it comes to a practical point of view, a power monitoring feature or protocol should be implemented first. So I think that the system designer of data centers should conduct an economic analysis if he would like to deploy the new operating scheme. Second point is the happening of response time violation, although it's very few. This is because we were exactly using the minimizing only speed scaling, which might be so tight that will cause a response time violation when a huge computational burst arrives. This problem will be easily solved just by allowing a slight margin to the derived value. I have some future research directions as well. First, I would like to embed this algorithm in real-world data center to practically show the effectiveness. From the research perspective, I've been seeking more theoretical approaches to find the true values of the decision variables. This is the end of my presentation. Thank you for watching this video.